Jordan's inequality is what we will use to prove Jordan's lemma. So let's continue the proof of Jordan's lemma, which is our main goal. We start by taking the integral from the limit that we want ultimately prove, which is the integral over c sub capital R of f of g times exponential of I a times g dg, where c sub R is a semicircle on the upper half of the complex plane with radius capital R. Here we can see the figure for this. And since we are integrating f of g over a semicircular arc, what we can do is convert this contour integral into an integral over an interval by using the polar representation of complex numbers. With this, g can be expressed by R times ei theta. So we can convert from this into this by using this. G is equal to, when G is equal to capital R times e to the I theta, then if we differentiating both sides by in terms of theta, we get this relation. So dg is equal to I times e to the I theta, d theta. So this part can be replaced by this, and g can be replaced by this. Since the radius of a semicircle is a constant, we can write the complex variable g as capital here larger times exponential of I theta here. Here, since we are integrating over theta here after conversion, we need to change the region of integration from the contour CR to the interval from 0 to pi with this polar representation of complex numbers for the arc CR. Let's now take the magnitude of this entire integral. Here you can see this part and this. Then let's record another fact. We see that magnitude of the integral is less than or equal to the integral of the magnitude. Okay? Here I wrote it. This less than or equal to the integral of the magnitude of this. This will be the same here. And look at this quantity. We see that for any pair of complex numbers G1, G2, we have this identity. Magnitude of the product of G1 and G2 is equal to the product of their magnitude. Okay? So we can apply this exactly same logic to the expression inside the integral to split up all the magnitude for this last magnitude. Yeah, then we get these three parts. For the last integrals magnitude, we can further split up to get the magnitude of the positive real constant capital R. First part will be just capital R, because which is the real number, and the magnitude of I, which is just 1 by definition, and the magnitude of E exponential of I theta, yeah, which is also 1. This is because here we can apply Euler formula to the exponential of I theta. We'll get cosine theta plus I sine theta, and the magnitude of this is just the square root of cosine squared plus sine squared. Okay, this is this, and we compute magnitude of this cosine squared plus sine squared, which is exactly 1.